when we are working with binomial expansions, it's really important that we keep that same approach that we had in APs and GPs, that we're working only with specific terms. So when you start learning binomials, you start learning full expansions and the coefficients of all of these terms. But we very, very quickly narrow that down to working with only one or two terms out of the expansion. So we're going to talk first about expanding in full, and then you'll see why we don't do it. Excuse me. Okay, so if we want to expand something in full, x plus 2 to the 5, for example. The full expansion of this would be, take our a position to the n, plus. Then we start with our combinations. So first one, 5, 1, a position to the difference, b position to the r, plus 5, 2, x cubed, 2 squared, plus 5, 3, x squared, 2 cubed. Everything going in brackets to protect any signs. 5, 4, x to the 1, so 2 to the 4, and then our last one is just our b position to the n. Then we would go through and we would simplify each term. So, x to the 5 plus 5, 1 gives us 5, x to the 4, 2, plus 5, 2 gives us 10, x cubed, 4, plus 5, 3 also gives us 10, x squared, 8, plus 5, 4 gives us 5 again, x 16, plus 2 to the power 5 is 32. Then we go again. X to the 5, 2 times 5 plus 10, x to the 4, 10 times 4 plus 40, x cubed, 10 times 8 plus 80, x squared, plus 5 times 16 plus 80, x plus 32. So we've got the whole thing, but it's taken us a few minutes to actually work through that full expansion. And that is not efficient. If we only wanted, say, the x cubed term, if this was all we wanted, okay, or maybe we wanted the constant term, okay, we wouldn't know if we were expanding the whole thing, where we're going to land up, and we've got all these other terms that we're calculating. We're taking time to calculate all these other terms we're never going to use. So the idea is that we go in and we calculate just what it is that we want. So if we wanted that x cubed term, we would have just calculated 5, 2, a cubed, b squared, and we would have gone straight to 40x cubed. If we were asked just for the constant term, then it would have been the 5 naught. 5 naught, x to the naught, 2 to the 5. Same as the 2 to 5 term equals 32. So the idea is that we don't want to waste time. For an AP and a GP, we wouldn't even dream of writing out the whole sequence. So just because a binomial is shorter doesn't mean you're going to write it out. Okay? You don't write out an AP, you don't write out a GP, and you don't write out a binomial. What you do is the same thing as you do for an AP and a GP. You just calculate the terms that you want to work with. So how do you know which one to do? If you don't go out the whole sequence, how do you know what R is and therefore what your powers are? And that's where we have a funky thing using understanding of indices. If we think about it, right, whatever is in our a term is always going to be raised to the power of n minus r. And whatever is in our b term is going to be raised to the power of r. And what is really cool is if you think about this in terms of what are the powers of x in these two positions. Just a reminder, we're talking here a plus b to the n. Okay, so when we're talking about the a position, it's what's on the left-hand side, the b position, what's on the right-hand side of that bracket. So let's say we wanted to make an x cubed term. If we had an x in this a position, the x and its exponent, when we do that calculation, see here, our x, so if we had x squared here, we would have x squared cubed. So we're always raising that x with exponent to the power n minus r every time we calculate this. So this would be any x in the a position. Same thing with here. If we had an x here, whenever we did any of these calculations, if there was an x or x squared or x to the minus 1, it would always be raised to the power r. So this is x in the b position. And if we take those exponents, we're not going to worry about the numbers that are associated in this case. We're just looking at which term to calculate. So we're just looking at the x's and their exponents. So on the right-hand side of our little equation here, we want to have the desired exponent. Whether it be a 3 for the x cubed term, whether it be a 2 for the x squared term, whether it be a 0 for the constant term, because x to the naught is 1. So it would disappear that x completely from our term that we're creating. Okay, so let's say we're doing the same one that we've been working with. We had x plus 2 to the 5. And let's say we want to build the x cubed term. We can check it against what we did in our expansion. What we would say is, in a position, we have just a plain x. So he doesn't have an exponent, he just sits there, and he would be to the 5 minus r. Then we would have something to the r. But there isn't actually an x in that position, so we can cross him out. We're going to make an x cubed. So we apply our laws of indices to the power. We really have a 1 hiding here, so we have x to the 5 minus r equals x cubed. Your laws of indices are so critical in so many different topics in AS Maths. So if we have x to the something equaling x to the something else, then something must equal something else. So therefore, 5 minus r equals 3. And 5 equals 3 plus r, and r equals 2. So now we would know that we want to calculate the term where n is 5 and r is 2. So if we actually then go to do that, we would have a term which says 5, 2. A position, x, to the difference. 5 minus 2 is 3. B position to the r. So 5, 2 gives us 10. X to the 1 to the 3 gives us x cubed. 2 squared is 4. And we end up with 40x cubed. And funnily enough, there is our 40x cubed. So you might find as you do more and more of these that you can start to see patterns, and you don't need to do this figuring out which terms to calculate. You can actually look at the expansions and know if I've got plain x, then this is what's going to happen. If my x is here, this is what's going to happen. But if you're a person who's struggling to see it, if you're a person who continues to struggle to see it, this little handy formula is going to help you to calculate the specific term each time. And that's why it is so brilliant, because it's always going to work, no matter how funky the sequences get. So let's have a look at another one. or 2 or 3. I've got a few examples. So what we're doing is we're always only calculating the terms we wanted. In some questions, they'll say calculate the first 3 terms. Then you calculate the first 3 terms because it leads on to something else in the next pieces of that question. But we're talking about, for example, things like now where we have 2 minus x to the 6, and we asked for the x squared term, or the coefficient of the x squared term. You'd still have to build that x squared term in order to see its coefficients. So we have a look at this and we say, okay, which term is it? How do I figure that out? So I have something to the 6 minus r times something to the r. Equals the x squared. So we're looking for that value of r. Now in this case, if we look in our A position, there's no x. So we're not using this bracket. The x here with his power, okay, he's a minus x, but that just means his coefficient is minus 1. We're not dealing with numbers at this stage, we're just dealing with exponents. And the exponent is a plain x, so he's just a x. So x to the r equals x squared. Therefore, in this case, nice and straightforward, r equals 2. So how would you calculate that x squared term? X squared term is going to equal nr 6, 2, A position to the difference, B position, and now we bring that minus because now we are working with the coefficients, and it is to the r value. So what is 6c2? 15 times 2 to the power 4 would be times 16. Minus x times minus x gives us x squared. So 16 times 15 gives us 240 x squared. So when we're looking for a specific term, there's 2 pieces to our calculation. And this is going to be the same thing over and over again. So let's have a go at 2 plus 3x to the 5. Let's find the x cubed term. So again, first we locate r. First position to the n minus r, 5 minus r. Second position to the r equals, we're building an x cubed. Again, there is nothing in this first position, so we're not going to use the first bracket. The x and his exponent in the b position is just a plain x. So x to the r equals x to the 3, and therefore r equals 3. So our x cubed term is going to equal 5, 3, 2 to the difference, 3x, because we take, of course, with our coefficient when we're calculating the whole term, to the 3. So 5c3 gives us our 10. 2 squared gives us our 4. 3 cubed gives us 27x cubed. Because remember laws of indices, that 3 must come in on both elements of the bracket. So 10 times 4 is 40 times 27 is 1080x cubed. So if they ask us for the coefficient, we can then conclude that the coefficient is just 1080. The whole term is 1080x cubed. But again, you can see that we're going straight to the term that we want rather than expanding out the whole sequence. And you actually get marks for selecting only the specific term and not calculating extra terms. So let's look at something a little bit more funky. 2 plus x squared to the power of 5. And let's do the x to the 8 term. So the same thing applies for r. First position would be to the 5 minus r. Second position would be to the r. And we're going to equal, in this case, x to the 8. In our first position, we have a 2, so we're not going to use it. In our second position, we have an x. Coefficient is 1, exponent is 2. So we need x squared. So again, laws of indices, to the power, we're going to multiply those powers. X to the 2r equals x to the 8. Therefore, 2r equals 8, r equals 4. So now we can go ahead and we can calculate that term. X to the 8 term equals, we're going to want the 5, 4. First position, 5 minus 4 is 1. Second position to the 4. So 5c4 is our 5. 2 x to the 8, which is 10 x to the 8 is the term that we're looking for. We didn't have to go calculate all those terms in order to get there. We just went straight there. Another one with something more interesting going on. X plus 2 over x to the 6. And we want the x squared term. So here now, we've stepped it up in 2 ways. We've got x in both positions, and we've got an underneath x. So first thing, what is our r going to be? Well, we're going to have something to the 6 minus r times something to the r, and we're going to build that x squared. So what goes in the first one? Well, it's a plain x to the 1. So just a plain x to the 1. In the second position, we don't worry about the 2 because he's coefficient. At this stage, just working with x in his exponent. What is the exponent for the x on the bottom of a fraction? This is now an x to the minus 1. So laws of indices. X to the 6 minus r, x to the minus r equals x squared. We can combine those. 6 minus r, so x to the 6 minus 2r equals x squared. X to the something equals x to the something else. Therefore, 6 minus 2r equals 2. 2r equals 4. R equals 2. And then we can go straight into just calculating that x squared term. NR, 6, 2. First position to the 4. Second position to the R. So 6c2 gives us 15. X to the 4. 2 squared is 4 over x squared is x squared. And we can see it starting to take shape. 15 times 4, our numbers give us 60. X to the 4 divided by x to the 2, magically enough, x squared. So, taking that time to figure out exactly what term you want, then you can very efficiently calculate what it is that's going on. So we've got one more example to fit in. X over 2 plus 2 over x to the 6, and we're going to go for the x to the 4 term in this case. So we do exactly the same thing. Hopefully you're now bored enough to never actually forget this. So we have 6 minus r, and we have second position to the r, and we're building x to the 4 in this case. In our first position, we have an x over 2. So the power of the x is just a plain x. The second position, x to the minus 1. And we don't worry about those 2's when we're just calculating r, because r, we're just understanding the exponents and how those exponents are going to combine to give the desired exponent. So x to the 6 minus r, x to the minus r equals x to the 4. X to the 6 minus 2r equals x to the 4. Therefore, 6 minus 2r equals 4. So 2r equals 2 and r equals 1. So then for our x to the 4 term, it's just a case of 6, 1. X over 2 to the 5, 2 over x to the 1. So we don't usually bother writing the 1. 6, 1, 6c1 gives us our 6. X to the 5 over 2 to the power 5 is 32. And there we have a 2 over x stays the same, no power involved. So we have 6 times 2 divided by 32 is our numbers involved in this term. That gives us 3 over 8. X to the 5 divided by x gives us x to the 4. So if we look at the format that they've used, and we match that format, 3x to the 4 over 8. Because we always want to, wherever possible, match the format that's been used in a question when we're giving an answer. So please make sure that this really, really hits home, that when we're working with binomials, we only want to calculate the terms that we need in order to answer the question. Sometimes you'll need more than one term. Sometimes you'll need the x squared term and the x cubed term. Sometimes you want the constant term and the x squared term. Depending on what it is that the question's asking and what it is you need to calculate, but the important thing, and a really, really important thing, is that you're only ever calculating those specific terms. You don't want to be throwing away marks because you're calculating extra terms. And also, calculating extra terms takes time, and you don't have time to play with to that extent in your exam. So you really need to make sure that you lump binomial expansions in with APs and GPs, where you're working with specific values. You're not working with the whole sequence. Even though when you start to learn these, that you are learning how to expand the full thing. It's only so that you understand how they work, how they go up and down, and all of those fun and lovely things about binomials. It's not how we actually end up working with them and understanding them, because our understanding of them as an entirety is so that we can pull out the relevant things that we need to work.